Well, we hope you've had a wonderful Canada Day weekend, and to our friends joining us south of the border, a very happy 4th of July. Welcome to this very special episode of EV Society's Canada Talks Electric Cars webinar. My name's Tim Burrows, and I'm one of many volunteers from across Canada who are helping with the transition to electric mobility. By becoming an EV Society member, you too would be helping others discover the many benefits of electrification. Visit evsociety.ca for more. So, in the good old days, if I can call them those, we could extend the life of our combustion engines by doing a bunch of things, changing the oil, changing the spark plugs, changing the filters, and other components, and doing that all on a very regular basis. Of course, one major advantage to owning an EV is the minimal level of maintenance that they require. This doesn't mean, however, that the way we care for and use our EVs has no impact on their longevity. EV batteries are, by far, the most expensive component in these cars, and everyone with an EV should want to maximize battery life. Understanding why and how our batteries degrade provides insight into operating regimes that will help keep them healthy and performing well for a very long time. Before introducing our guest speaker, I invite you to ask questions using the Q&A button on your Zoom toolbar. Remember too that you can upvote other submitted questions so we can address the most pressing ones in the limited time that we have available. So today we are sincerely honored to welcome back Dr. Jeff Dahn, a premier authority and researcher of lithium-ion battery technology. Professor Dahn is with the Department of Physics and Atmospheric Science and the Department of Chemistry at Dalhousie University. Dr. Dahn is recognized as one of the pioneering developers of the lithium-ion battery that is used worldwide in laptop computers, cell phones, and many other devices, including electric cars. Dr. Dahn, are you there? There we go. Thank you very much for joining us and welcome to another episode of the webinar.
Happy to be here, Tim.
Well, I know that you have a lot to cover, and if there's time at the end, I think you're going to take a little bit of a dip into another interesting topic, which is the what we might expect from the up-and-coming sodium-ion battery tech, which I think you've been doing some work on. So I'm going to get out of the way and let you have at it.
Okay, I think hopefully people can see my screen and hear my voice.
It's all good.
So great. So my title's a little bit different than Tim's. Really, it's about what you should do to maximize the battery life of your EV. So I want to start first by talking a little bit about the basics of a lithium-ion battery. Lithium-ion battery is a conceptually simple device, has a negative electrode comprised of graphite on a copper current collector, and normally a positive electrode, which is a lithium transition metal oxide on an aluminum current collector. And we're showing a highly expanded view of these electrode materials to show the individual atoms here. And what you'll notice about graphite is it's a layered material with layers of carbon atoms tightly bonded and spaces between those layers where little atoms like lithium can fit. The same is true of the positive electrode. You have transition metals sandwiched between layers of oxygen and spaces where lithium atoms can fit. And during the charge and discharge, the lithium ions move from one electrode to the other through the electrolyte. And when this happens, there's almost no structural changes to the positive and the negative electrode, which allows for many, many charge-discharge cycles to take place. So the lithium-ion battery, they have the highest energy density of any ambient temperature rechargeable cell. They have a long lifetime. They have almost no self-discharge. They come in convenient sizes and shapes. They're affordable. and they can be designed with a short recharge time. I'm going to be talking today mostly on lithium-ion batteries that have what are called NMC as the positive electrode material. And NMC means it's a lithium nickel manganese cobalt oxide. And the class of these materials, like NMC 532, means the nickel is 50%, the manganese is 30%, and the cobalt is 20%. So X would be 3 and Y would be 2 in this formula. And then you can have a material with slightly more nickel content, NMC 622, or even more, NMC 811. Now, there are some issues with lithium-ion batteries, which I'll talk about now. It turns out that each of the electrode materials, both the positive and the negative, are very reactive with the electrolyte in the charged state. When you realize this, you think, how the heck could this thing even work? But it turns out that during the first charge of the lithium-ion battery in the factory, there are reactions that take place between the electrolyte and the electrode materials as they're charged. And in that reaction, some of the reaction products form protective layers on the electrode materials, and they allow the cells to operate. And this is kind of a miracle, actually. But it turns out that these protective layers aren't 100% perfect, and slowly over time and at elevated temperature, the cells can degrade. Another thing that's important to realize is that each of the electrode materials expands and contracts on the order of 10% during charge and discharge. And this means that the electrodes, which are made of these materials, have to be able to withstand this continual volume change. So it turns out that the voltage of a lithium-ion battery varies with its state of charge. So here I show the voltage versus state of charge. 100% state of charge is the highest voltage, and as you discharge, the voltage goes down. So this is a curve for a typical NMC 532 graphite cell. And it turns out that when the voltage is higher, the positive electrode is more reactive to the electrolyte in the cell. Or if you like, when the state of charge is closer to 100%, the positive electrode is more reactive. And EV users and researchers often operate electric vehicles under restricted state of charge ranges. For example, you might charge to 60% and discharge to 40%. So this is what I mean by a restricted state of charge range. So now I'm going to go back to 2014 and talk about a paper, a really, really nice paper from a research group in Aachen, Germany, that describes some of the major failure modes of lithium-ion cells. So this is the paper by Madeline Ecker, and the professor is Dirk Uwe Sawyer. And they're characterizing lithium-ion cells from 2014. And things have improved since that time, but the main messages in this paper are still valid. So this is a graph that shows the capacity of a lithium-ion cell, how much amp hour capacity it can deliver as a function of time while the cells are being stored at 50 degrees C at various state of charge. So if you store the cells at 100% state of charge at this very high temperature, you can see that they degrade very rapidly. And by contrast, if you charge the cells store the cells at 10% state of charge or 20% state of charge, things degrade much more slowly. And the rate of loss is greater at the higher states of charge. And this is because there's a higher voltage at the positive electrode, and it just becomes more reactive with the electrolyte under those conditions. Now in this graph, they show what happens to the normalized capacity versus storage time, where the cells are stored at 50% state of charge, but at different temperatures. And you can see that at 50 degrees C, things degrade much more rapidly than at 40 degrees C and at 35 degrees C. And this is because the virtually all chemical reactions accelerate with temperature. And these are the parasitic reactions between the charged electrode materials and the electrolyte that are accelerating as the temperature increases. So this is a consequence of the fact that the protective layers on the electrodes are not 100% perfect. And this graph shows what happens to the normalized capacity when you're actually doing charge-discharge cycling, not just storage. So here, the cells are being charged in 1 hour and discharged at 1 hour at a temperature of 35 degrees C. So when the cells are going from 0% state of charge to 100% state of charge, you can see that they degrade in about 100 days. But when the cells undergo restricted state of charge range cycling, so like here from 40% to 60%, you can see that they do much, much better. They're lasting 400 days to about 85% under this aggressive cycling, 1 hour charge and 1 hour discharge continuously. So you might ask the question, why do they do much better under restricted range cycling? And this is because the volume changes that take place in the electrodes, the magnitude of those changes are more or less proportional to the extent of the state of charge range. So when you're going from 0 to 100%, the volume changes in the electrode materials are maximal. And when you're going from 40 to 60%, you've limited those volume changes to about 20% of what they would be over the full range. If you look at the very top, you'll see the data for a cell that's not being charged and discharged at all, just being stored at 35 degrees C. And right below it is the data for a cell that's being just tweaked over a 5% state of charge range. It's virtually the same as a cell that's doing nothing. Now, it's interesting to think about what the range of a vehicle would be for this situation. So they tell you that 400 days more or less corresponds to 3,200 equivalent full cycles. So 400 days of cycling continuously between 40 and 60% would be equivalent to 3,200 equivalent full cycles. And if it were a 400 kilometer vehicle, that would translate to 1.2 million kilometers. But to get that, you would have to limit yourself to short drives of 80 kilometers or so repeatedly to get to this type of total range. And this is huge. But if you're doing 0 to 100% cycling, you'll see that your total range would be much, much less. So I want to make a mini summary at this point. Lithium-ion cells lose capacity during storage. This is mainly because of reactions between the lithium atoms intercalated into the graphite negative electrode and the electrolyte. This consumes lithium atoms that could otherwise be contributing to the cell capacity. And this process accelerates at high temperature and also when the cell voltage is higher. So there's a message here, and it is, if you go away in the summer, store the battery in your vehicle at a lower state of charge, like 30%. So you still have, some driving range when you come back from your trip. This way, the pack will be exposed to the high temperature in the summer at a low state of charge. Lithium-ion cells lose capacity during charge-discharge cycling. So the processes that occur in number 1 are also occurring, but these can accelerate due to microcracking of electrode particles due to the volume expansion and contraction during cycling. So the particles in the electrodes are expanding and contracting, and that can lead to them cracking and exposing new surface that has to be covered by reaction products. And microcracking gets worse when the depth of discharge is larger. So if you want to make a better lithium-ion cell or one that lasts longer, you need to eliminate microcracking and limit the reactions between the charged electrode materials and the electrolyte. It's really this simple. So let's see how to do that. So I don't know if the positive materials in my EV are subject to microcracking. So what can I do? And I don't know if I have an excellent lithium-ion cell in my EV or not. Maybe I have something of the 2014 vintage, which is pretty good, but not as good as things today. So let's understand the origin of microcracking better to see how to avoid it. So this figure shows the typical morphology of NMC positive electrode particles. I'll start at the left. You can see these little spherical balls. There's a 30 micrometer scale bar. So these things are 15 micrometers or so in diameter. And if you zoom in, you can start to see that they're not actually a smooth surface. If you zoom in even more, you can see that each of these particles that we call a secondary particle is made up of millions of very small crystallites that we call primary crystallites. And this morphology is used for a number of reasons, but one of them is to get fast transport of lithium from the surface into the middle of the particle where it is stored. The lithium can travel more quickly along the boundaries between these primary crystallites. So fast lithium diffusion along the grain boundaries. Excuse the spelling error there. So why does this microcracking occur? Well, if you go and look at the atomic structure of an NMC material, you can see here the transition metal atoms shown in solid black, the oxygen atoms shown larger in gray, and the lithium atoms shown in white. And as the lithium is removed and reinserted into the structure, these vectors called A and C change in length. These are the characteristic vectors that describe the crystal structure. It just repeats again and again and again. But the distances between these neighboring transition metal atoms and the distance between the layers changes as the lithium content changes back and forth. So how do these things change as the lithium content changes? So here I show a graph that shows how this A-axis and how this C-axis changes with the lithium content in NMC 622. And I put on the top axis where you would be if you were 0% or fully discharged, and in a typical EV where you would be at 100% charge. And you can see that there's a significant variation in both of these parameters. But what is most concerning is one of them shrinks and one of them expands during this change in the lithium content or change in the state of charge of the material. So the volume changes are anisotropic. And what this means is if you have a particle that's comprised of all these primary particles, as this expansion occurs over many charge-discharge cycles, it can lead to cracking of the particle along the boundaries between the primary crystallites, because some of them will have their A-axis this way, and the next particle will have their A-axis this way, and they'll be doing different things, and eventually that interface will break. So I want to show you how to avoid microcracking if you have a positive electrode material that is susceptible to microcracking. So here I'm showing a graph that shows for a small lithium-ion cell, the discharge capacity versus time. So 20,000 hours is about 2 1/3 years roughly, while they're being charged and discharged continuously with a 3-hour charge and a 3-hour discharge at C/3. So then green are cells that are undergoing 100% state of charge range or 100% depth of discharge. In red, 75%, in blue, 50%, and in black, 25%. And you can see the number of cycles that have been accumulated during this 20,000 hours of testing. a large number of charge discharge cycles. These data points up near the top represent every 500 hours for all of the cells, we did 100% state of charge range. So we call this a checkup cycle. So we're cycling along at 25% depth of discharge, but every 500 hours we do a checkup cycle to see what the capacity would be if we did 100% state of charge cycle. And when you look at these data, you can see clearly that the green, where you're doing 100% state of charge every time, is worse than the red, is worse than the blue, and the black, where you're doing these 25% state of charge cycles, the capacity decline is very minimal over this 2.5 years roughly of testing. So all these cells are undergoing the same amount of charge throughput. They all would have driven a vehicle the same distance, all about 1.5 million kilometers. But at the end of this time, the battery that operated over the 25% depth of discharge has lost far less capacity than the battery that's operating over 100% depth of discharge. So what this means is lots of short drives followed by charging is better than charging infrequently. This is a summary of the data on the previous slide, which shows the fractional capacity loss as a function of the depth of discharge that was taking place during those cycle tests. So you can see a sort of a linear progression here. After 2.5 years of continuous testing, cells that did the majority of the testing at 25% depth of discharge lost only 8% of their capacity. And by contrast, cells that worked at 100% DOD lost 27% of their capacity. So the take-home message number one is charging frequently to ensure lots of low depth of discharge cycles is better than charging infrequently, leading to high depth of discharge cycles. Long drives from time to time are fine, but charge when you can is the message here. So it's really interesting to see what's happened to the positive electrode materials in these cells after this 20,000 hours or 2.5 years of testing. So it turns out that you can do X-ray computed tomography, almost like a CT scan at the hospital, to look inside your body for problems. And we can do the same thing to look inside lithium-ion batteries to look for problems, but with much higher magnification. So this is a X-ray CT of one of the cells that was being tested there. And just for it's a very small lithium-ion cell. That's a 1 millimeter scale bar. And Toby Bond at the Canadian Light Source in Saskatoon did these measurements. And then he zoomed in, and he zoomed in again, and he zoomed in again. So in this panel C, I'll explain what we're looking at here. So this very bright line is the copper current collector of the negative electrode. And this dark material on either side is the graphite layer for the negative electrode. And then you can see the little spherical balls on the positive electrode next. And this gray line down the middle is the aluminum current collector of the positive electrode. And then the other side has also coated with positive, and then this whole structure repeats. You can't see it in this image, but when you blow up even more, you can see this line right here. This is the separator that separates the positive from the negative. And when you really zoom in, you can see the positive electrodes particles very nicely. And now we're going to zoom in even more and then look at 3 different cells. So what we're doing now is we're looking at a cell, the positive electrode in a cell that's only done what's called the formation cycle. This means directly from the factory as you would receive it. And then we're looking at a cell that's operated at 25% depth of discharge for 2.5 years. Okay, so when you look at this particle, it's not obviously the same particle. We tried to find a large particle to compare. There might be some evidence of microcracking here, but very little. the image between the fresh cell and one cycled at 25% DOD for 2.5 years or 16,000 cycles are not very different. But if you look at the positive electrode in a cell that's cycled at 100% depth of discharge for 2.5 years continuously, and this was 3,000 charge discharge cycles, these particles have virtually disintegrated. And to be honest with you, it's surprising to me that the cells still work at all when the positive electrode is in this condition, but they do. They were still delivering about 80%, or maybe it was 75% of their original capacity. But you can see the advantage of doing low depth of discharge cycling very clearly in this image. It's quite spectacular. Okay, so if we have the ability to charge at home easily, we can operate lithium-ion cells in this mode where they're seeing 25% depth of discharge most of the time. And this will absolutely prolong battery lifetime. But many EV owners cannot charge at home, and they use public chargers all the time. And that means they want to charge infrequently for convenience. And even if you do that, you're still going to get very long lifetime. It just won't be as long as if you do what we're suggesting above. So with this in mind, it's very important to understand how to eliminate this microcracking altogether. So there's a really famous researcher in Korea named Young Kook Sun. He's at Hanyang University, and he, among others in the lithium-ion battery community, including myself, are promoting what is called single crystal positive electrode materials. So what he shows here is what happens to the traditional positive electrode materials after 100 charge discharge cycles. You see all this microcracking. But if you use single crystal materials, which are not made up of a whole aggregation of small particles fused together, but each particle is just one single crystal where the crystal axes are spanned throughout the whole particle without interruption, then this thing will just expand and contract as a whole, and there's no ability for microcracking to occur. So this is after 100 charge discharge cycles, and there's no microcracks in any of these materials at all. So what happens after more cycles? So we published this paper in 2019 where we use single crystal NMC 532, and this is a cross-sectional scanning electron microscope image of the positive electrode. After 5,300 cycles, the cell had 97% capacity retention. And you won't see any microcracks in these particles. This one big one that we've been following, we don't know if this crack was here from the beginning or whether it did form during the charge-discharge cycling. But these single crystal particles really eliminate microcracking, which leads to, some of the problems in cells. So here I'm showing you 5 years of testing on single crystal NMC 532 graphite cells. These cells are charging in 1 hour and discharging in 1 hour. They've been going for 5 years. They're going from 0% fully discharged to 80% charge, 16,500 cycles with virtually no degradation. If every cycle represented 400 kilometers of driving, this could power a vehicle for 6.4 million kilometers. And nobody's going to drive a vehicle that long. So this type of technology enables vehicle to grid operation, where your vehicle's plugged into the grid when it's not driving, and the power utility can charge it to store energy from renewables and discharge it, say, for example, in the evening when there's no sun, to help power everybody else's homes. If you were to use this in an energy storage product, 1 cycle per day, 16,500 cycles, that represents 40 years if the battery was operating at 20 degrees C. Another thing that's really interesting is in our little cells, they have what's called a gas bag on the side. Now, a real lithium-ion cell would have this cut off and the cell would be would be sealed right here. But this gas bag is really interesting because as the cells undergo these unwanted parasitic reactions between the positive, between the electrode materials and the electrolyte, some of the reaction products can be gas, and the gas bag will puff up. So it's kind of like a canary in a coal mine. It tells you when there's a problem with your cells. If you start to see the gas bag puffing up, it means that you have these unwanted reactions going on. So we're going to take a view in along this arrow and take a look at this gas bag to see if it's puffed up for this cell. So this is the cell number 81607. And here's the gas bag sort of curled vertically. You're looking in at the direction of this arrow, and it's absolutely flat after 5 years and 16,000 cycles. So that means virtually no degradation in the cell at all. It's incredible. So the take-home message here, number 2, is if the lithium-ion battery in your EV uses single crystal positive electrode materials with a moderate nickel content, like NMC 532 or 622, then you really don't need to worry about microcracking the positive electrode at all. So in this case, you can charge when you like. And your battery is eminently suitable for vehicle-to-grid applications where many charge-discharge cycles will be applied to the battery while the car is parked. After all, you've got access to millions of kilometers of driving you'll never use. So the lithium-ion cells I've described up to now with these NMC 532 and 622 will enable a moderate range EV of 400 to 450 kilometers. But many EV owners want longer driving range. So what do we do for them? Well, we need to use lithium-ion cells with a higher energy density. And how do we get there? So here I show you the voltage versus what's called specific capacity for 3 different single crystal materials: NMC 532, NMC 811, and NMC, where the nickel content is 94%. The manganese and cobalt contents are each about 3%. And what you'll notice, these all are being charged to 4.4 volts. And if you look and see what the specific capacity is when you get to 4.4 volts, 532 is less than 811, and nickel 94 is about the same as 811. So you can pack more energy density into the battery if you switch from 532 to 811. You get more milliamp hours per gram of material, which means more amp hours in the battery per kilogram of positive electrode material that you pack in. So you will move to materials with higher nickel content to get longer driving range. Now, when you look at these curves, you'll notice there's one striking difference. These 811 and this nickel 94, they have this extra sort of plateau near the top of the charge, right? You can see it, and 532 does not. What's going on here? It turns out that the plateau in the voltage curve coincides with a large volume change in the positive electrode material. So this is a place where the positive electrode volume changes rapidly, and it's more likely to create microcracking if you go back and forth across this plateau. So you want to avoid this for long lifetime cells. And you could say, well, what if I make single crystal material? What happens then? Well, it turns out also that there's a tiny amount of oxygen released from the positive electrode during this plateau. And this oxygen can react with the electrolyte and cause degradation over hundreds of charge-discharge cycles, okay? So over hundreds of charge-discharge cycles, capacity loss and power loss can be detected. So if you want to really maximize battery life, you want to avoid this plateau. So what do? Well, all you have to do is stop the charge before you get to this plateau, which means charge to 75% to avoid large volume changes and this oxygen release. Charge to 74%. So if you have a long-range electric vehicle, chances are it has one of these high nickel content materials, And you can, if you charge to 75%, you'll avoid this large volume change and this tiny oxygen release. So there's a really good chance you're not going to know what the positive electrode material is in the lithium-ion battery of your car. So you can just say, oh, well, I don't know, but I want to be safe, so I'm going to charge to 75% most of the time. Here's an example of showing you the advantages of charging to 75%. So this is NMC 811 graphite cells. So typical lithium-ion cell operated at 40 degrees C with a 3-hour charge and a 3-hour discharge. Continuous cycling, 3,000 charge discharge cycles. If you charge to 4.06 volts, which is 75%, you can see the capacity is less than if you charge to 100%, which is 4.2 volts for this cell. But you can see when you charge 100%, the cell capacity degrades more rapidly than if you charge the 4.06 volts. And if you look at the normalized capacity, you can see after about 2,500 cycles, you're down to 80% when you charge to 100%. But after 3,000 cycles, you're down to above 90% when you charge to 70%. What's really also interesting is we plot here what's called the normalized polarization. This is very similar to the battery internal resistance, which controls the power capability of the battery. And when you're charging to 75%, this internal resistance doesn't increase at all. So it means the power capability of your vehicle will not be compromised as it ages. Whereas when you're going to 100%, you can see the internal resistance has about doubled over this period of time. But this is an incredible number of charge-discharge cycles, right? And so both of these scenarios would provide impressive vehicle life. But if you limit to 75%, it will provide opportunities for vehicle to grid and also for second use at the end of when your car rusts away, the battery's still going to be in very good condition. So take-home message number 3 is, if you have a long-range EV which has cells containing nickel-rich materials greater than 70% nickel, then charge only to 75%, a full charge if you can. But you may not be able to determine the exact chemistry in your cells. Turns out that on YouTube, there's teardowns, and maybe people will take apart the cells in your car and do all sorts of chemistry to figure out what the positive electrode material is. And doing this avoids the large volume changes that can occur, which over many years can cause capacity loss, microcracking is minimized, and oxygen release from the positive electrode materials avoided. So if you're like me, or maybe just have your ear to the ground, you'll be hearing a lot about sodium-ion batteries these days. So what's the status? And I thought I'd spend a few moments on that just before I could conclude. So here are photographs of these cells that we work on in our lab. The cells all have the same area, and they all have the same capacity. They're each about 200 milliamp hours. But when you look at them, you'll see the highest energy density lithium ion is the thinnest. And here's a 622 cell, it's thicker. Here's a lithium iron phosphate cell, it's even thicker. And here's a sodium ion cell, it's the thickest of all. So they all have the same area and the same capacity and roughly the same voltage. So this sodium ion cell will have by far less volumetric energy density than the highest energy density lithium ion, at least a factor of 2 worse, and worse than LFP even. So what this means is, if you're going to use the sodium ion cell, you're going to pay an energy density penalty, but it will probably be suitable for short range electric vehicles like 300 kilometers, maybe 250, and it should be suitable for grid energy storage. The real motivation for sodium ion is long-term sustainability, because a lot of us are worried about whether there'll be enough lithium into the deep future as we start to really electrify everything in the world. And in addition, you can make a pretty good positive electrode material for sodium ion with a minimum amount of nickel, which is, again, a concern in the deep future. Just to show you some performance data for sodium ion cells, this is at 55 degrees C, which is very aggressive and causes cells to die rapidly, running at a 3-hour charge and a 3-hour discharge. We started working on sodium ion cells, and the first electrolytes that we used, the blue, performance was okay, but the cells generated gas. And then we switched to another electrolyte that improved the performance, but we still got gas. And then we learned if we added a special ingredient to electrolyte 2, we could eliminate the gas, and you can see that things look like they're going to go really well. So we and others around the world are demonstrating good lifetimes with sodium ion, and a number of Chinese companies and also a company from India have announced commercialization plans for sodium ion. So I'll summarize what we've learned here to maximize battery lifetime. Lithium-ion cells degrade during the summer, during storage at high temperature and high states of charge. If you're away for a period of time in the hot summer, leave your vehicle near 30%. Eliminate microcracking. Stick to low state of charge ranges. 25% is awesome. That's difficult for people who cannot charge at home. Well, that's okay. The battery will still outlast the car if you follow the next 2 rules. Eliminate oxygen release from high nickel materials. Stay below 75% state of charge when you can. And eliminate the large volume changes to eliminate microcracking if you have a non-single crystal material. Again, stay below 75 state of charge when you can. So if you combine all this together, and assuming you don't have any idea what kind of battery you have, if you operate between 70 and 45% for the majority of the time, that's ideal. Store at 30 when you're going away for long times in the summer. And then finally, if your cells have single crystal positive electrode materials with a nickel content less than 70% and appropriate graphites, you don't need to be concerned at all. And your battery is suitable for vehicle to grid use without any issue at all or any concern. And the same is more or less true for cells with lithium iron phosphate positive electrodes. Those are quite long-lived batteries, and I didn't talk about them today just because of lack of time. Okay, so anyway, I'm done, and I'm going to stop sharing my screen so that we can have a Q&A session. If I can figure out how to do that. Here we go. Somebody did it for me.
There you go. Technology at its best. Well, I'm going to sneak in a question just to give me some perspective and context. So if for example, you are going to go away for a month in the middle of a hot summer, would it be worth deliberately running your battery down from, let's say you're normally keeping it at 75%, because we now know that's kind of the ideal max. Would it be worth running it down to 30% before I go away for a month, or just leave it unplugged and let it trickle down on its own?
If you leave it unplugged, it's hardly going to trickle down at all over that time period. I would just say you're thinking, okay, I'm going to be going away in 3 or 4 days, right? And you just plan your charging plan so that when it's time to go, your car is sitting there about 30%. Yep. Right.
Fair enough. Great. All right. I'm going to introduce Sean Hart. Of course, Sean is a longtime EV Society board member, and he's kindly volunteered to sift through. We've got quite a few questions, as we would expect. And Sean, I'm going to let you take it away, please.
Great. Thanks, Tim, and thanks, Dr. Dahn. Just a reminder to everyone, if you see a question on the Q&A list that you like, give it a thumbs up and it'll rise to the top. So we'll ask the questions with the most thumbs up first. And I'll apologize, we won't be able to get to all the questions, but we'll get through as many as we can. Just one, if I could start with Dr. Dahn, just to clarify, when you're talking about like 100%, like the range state of charge, you're talking about the cell specifically, right? So if 100% charge in a vehicle, for example, isn't 100% charge in the cell, right? The manufacturer leaves a little bit of buffer at the top and bottom. Is that correct?
I'm talking about 100% basically in the vehicle.
Oh, okay.
So
Okay.
when I was talking 100%, I was referring generally to 100% in the vehicle. Yeah.
Okay. All right. Great. Thanks. Thanks for clarifying that. Yeah, and feel free to skip any questions that are either not relevant or that you can't answer. That's fine. The next question is about the battery capacity with respect to temperature. You were talking about the warmer temperatures. What about the colder temperatures? You know, if you're at, you know, you're in Canada, it's winter. How do the colder temperatures affect battery life?
Yeah, cold temperatures are good. The colder it is, the longer your battery will last, as long as it's not doing anything, right? If it's just sitting there in the cold, all these degradation reactions become virtually nil. And, you know, to have the battery operate in the cold, the charge and discharge rates that it can support are very, very low. So what happens in your vehicle is the battery gets warmed up in the winter so that it can operate well. But when the car is parked in the cold, you couldn't ask for anything better. Believe me, it's really wonderful.
Okay, great, thanks. In terms of charging speed, so there's a few questions on this one. Is it either better or harmful to fully charge using level 2 versus level 1 versus DC fast charging? Does that make a difference?
Yeah, typically it won't make much of a difference. And this is because the vehicles themselves will control the charging current when you go to a DC fast charger so that it won't charge faster than the battery can handle. You know, I do mostly level 2 and level 1 with my EV, and I'm not concerned at all about that, because even level 2 is about an 8-hour charge for my car, and that's perfectly fine.
Okay, great, thanks. Next question, another one in the winter. If you're going on vacation in the winter, should you also lower the state of charge of your battery before you leave, or does it not matter as much when it's in the winter?
Won't matter in the winter.
Okay, perfect. I guess you kind of touched on this a little bit, but a few questions about how to know what the chemistry is of the battery in any particular EV. You mentioned YouTube. Any other sources for that?
You send me a confidential email. Maybe one way. No, but really, actually, you know what's fun? If you're not buying a Tesla, you know, and you go to a dealer, ask them what chemistry is in the battery. Ask the salesman. They won't have any idea. It's quite funny. They should have an idea, but they don't. Okay. Yeah, it's sometimes very difficult to find out exactly what you have. And it really, the information should be available, because it's like, as Tim said, in the so-called good old days, you would know exactly what kind of an engine you have in your vehicle. You have a 4.3 liter turbocharged, fuel injected, whatever, right? But nowadays, electric vehicles, you know, if you have a lithium-ion battery, that's basically what you're told.
Right. Okay. Yeah. Thanks. You talked a bit about the single crystal, like NMC cells. Is that actually available in any products yet? And is there any challenges in producing those?
Yes, that is available in products. I actually had a PowerPoint sent to me today by a Chinese manufacturer of single crystal materials, mass production scale, 100,000 tons roughly per year total from all their plants. And they gave a list of their customer, the battery customers that use their single crystal material. So when you look at those battery companies, you say, aha, company X supplies batteries to car maker Y, and so on, right? So you can tell who has single crystal materials in their vehicles. And there are quite a few vehicles nowadays that have single crystal materials in them.
Okay. Wow. Yeah, that's good to know. The next question is I don't know if this is fair for you, but it's about the warranty that OEMs provide on their batteries. Why is the warranty only 8 years if these batteries can last so much longer than that?
Yeah, I think the reason for that is they're really covering the 99th percentile of really aggressive users that are going to go 0 to 100% every day. So maybe it's a traveling salesman or whatever, and you've got to deal with that scenario. But here's an example for you. There's a fellow here in Nova Scotia named Kurt Sampson. In fact, many of you may know this guy. He's the president of the Electric Vehicle Association of Atlantic Canada. He has a Tesla Model S. I think it's 2016. It has 420,000 kilometers on it. It still has 84% of its battery left. So it's way beyond the warranty, way beyond. And his frame and everything's probably going to fall apart long before his battery, and it'll still be fine. Stick it in second life, And I think this is the case for most EV users. You're going to learn that the battery's going to last a long time.
Yeah, no, thanks for that. And I wish it was easier to get that message out, because I hear that comment all the time as well from non-EV owners, that they're worried the battery's going to die after a few years.
Well, the early days, right? The Nissan Leaf in the Arizona and so on, the battery was air cooled, not cooled with a heat pump, and the chemistry in that battery was not good at high temperature. And some of those cars were losing 27% in a year, right? But I know Nissan Leaf owners. Actually, my neighbor has a Nissan Leaf in Canada, and it's basically fine because it's not exposed to these enormous temperatures that cause this degradation.
Right. Yeah. All right, so the next question is from Doug. He heard that the optimal state of charge for a lithium battery is 58%. I'm not sure there is a particular reason for that number.
I don't know. I mean, it may be the case for some particular chemistry that 58% is absolutely perfect. But, I think I can give you, sound reasons why 75% is a good upper end. I can give you sound reasons why, smaller state of charge swing is better. And if it turns out that for you, 58% going back and forth, 25% from there is suitable for your situation, by all means. The lower the state of charge, the better, right? But 75% is a pretty good number. It leaves you in a situation where, say you get a call from your son or daughter who's 200 kilometers away, their kid's really sick, got to take them to the hospital, and the other child needs someone to look after them, and you've got to zip over there immediately. So better to have that buffer.
Yeah, thanks. And another question about winter, I guess, just is there any change to that recommendation, whether it's cold or warm, that 75% recommendation?
No, not really. I think that's okay. The hotter it is, the better it is to be lower in state of charge. But in Canada, we don't really see these extreme temperatures too much throughout the summer. How many days per year is it 40 degrees? Not too many. So, my answer would be different if we were talking about Phoenix, Arizona or something. And I would say, keep it at lower state of charge more.
Right. Thanks. Next question is about V2G. You touched on that a little bit. Are you aware of V2G being kind of used at a larger scale anywhere in the world, other than, you see a lot of very small kind of test cases for it? But
not yet. There's a lot of pilots happening. Actually, it's interesting. Prince Edward Island just bought several Lion Electric school buses from Lion Electric in Quebec. And the whole idea is to go V to G as a pilot project in PEI. That's going to be really cool. And that's kind of stuff springing up all over the place. And it's just a matter of time before people, utilities, governments realize it's going to be super important to harness all this battery capacity in the cars for storing energy from solar and wind when it's available. You know, that's just a huge amount of battery asset on the ground that we need to deploy.
Right. Thanks. Okay, the next question. So someone's really you're taking that 75% number to heart, but his car only has 20% increment. So is it better to do 60% or 80%? I guess 60.
Really? You only have 20% choices? Well, I would say if you're driving in the city mostly, and then I would say pick the 60. But if you're going on long drives more often, then take the 80.
Okay.
One more, I think, Sean, and then we're going to have to call it a wrap.
Okay. I think this one was answered.
Have we covered them?
Do you have any thoughts? Yeah, there's a few answered here. Any thoughts on recycling? Like, you know, will different battery chemistries have different values, you know, at the end of the car, you know, or any implications on recycling?
Well, I think, you know, as lithium-ion batteries and vehicles eventually die, you're going to have to recycle virtually all of them, because the mineral content in a pile of lithium-ion batteries is enormous compared to what it is in the earth. You know, it's just an urban mine. But my goal is to make them last so darn long that we're not talking about recycling for 50 years.
Love it. I think that's probably the goal of everybody who buys one too. So, no, that's awesome. Well, thanks, Sean, for taking us through that. And Dr. Dahn, I can't thank you enough. We really, really appreciate you taking the time and spending it with us and sharing just this amazing amount of knowledge that you have in the subject. And I know I can tell by the attendance numbers that people hung in there and were just taking that all in. And again, we really do appreciate it.
Yeah, you know, we should do one sometime where it's almost all Q&A, because I think that's really quite a fun part of this whole thing.
I agree. It's always a mixed bag. You have to cover both ends of things, but it was great.
All right.
Thank
Bye,
you.
everybody. Enjoy driving your vehicles.
You bet. And you too, yours.
Yeah.
All right. So now that we have a better understanding of how to take good care of our batteries, we plan to welcome next time Chief Operating Officer from one of Canada's best charging platforms, ChargeHub. And he'll be joining us on the webinar. Next month, we'll be joined by Francis Dubois, who will pull back the curtain and explain how their company is about to make it simple for electric vehicle drivers to charge right across Canada on a wide variety of different networks using just one account. So that's been, I know, a bugaboo for a lot of folks through this transition to electrification, and it'll be interesting to hear their answer and their solution to that. So please do mark the date. It's Tuesday, Tuesday, August 1st, always at 7:30 p.m. Eastern Standard Time. So on behalf of the entire webinar team here at EV Society, I want to thank you all for joining us on today's episode, and also thank you for your continued support of this webinar. From all of us at EV Society, until next time, stay well. This will conclude today's webinar.